In organic chemistry, molecules often face a choice between two paths, substitution or elimination. When we look at tertiary alkyl halides, the structural environment dictates which mechanism will dominate. Today, we examine why one path is almost always blocked. A tertiary substrate features a central carbon bonded to 3 other carbon groups. This creates a highly crowded environment. This physical crowding, or steric hindrance, is the most critical factor in determining the reaction outcome for these specific molecules. The SN2 mechanism requires a backside attack, where the nucleophile hits the central carbon directly. However, in a tertiary halide, the bulky methyl groups act like a shield, making it physically impossible for the nucleophile to reach the target. Because of this extreme crowding, the rate of SN2 reactions for tertiary alkyl halides is effectively 0. Even with a strong nucleophile, the transition state is too high in energy to be reached under standard laboratory conditions. If the center is blocked, where does the reagent go? It attacks the periphery. In an E2 mechanism, a strong base targets a hydrogen atom on a neighboring carbon, known as the beta hydrogen, which is much more accessible. The E2 reaction is concerted, meaning everything happens at once. The base pulls a proton, the carbon-carbon double bond forms, and the leaving group departs. This bypasses the crowded central carbon entirely, making it highly favorable. Comparing the energy profiles, the activation energy for SN2 on a tertiary center is prohibitively high. The E2 pathway provides a much lower energy transition state, allowing the reaction to proceed rapidly toward the elimination product. The nature of the reagent matters. While a strong nucleophile might want to perform SN2, the tertiary structure forces it to act as a base instead. If the reagent is both a strong base and bulky, E2 becomes even more dominant. Let's look at an example. When tert-butyl bromide reacts with sodium hydroxide, a strong base, we don't get an alcohol. Instead, we get isobutylene. The hydroxide acts as a base to eliminate HBr from the molecule. In the transition state, the double bond is already partially formed. Because tertiary substrates lead to more substituted alkenes, the transition state is further stabilized by hyperconjugation, making the E2 path even faster. Using a bulky base like potassium tert-butoxide ensures that only elimination occurs. The reagent itself is too large to act as a nucleophile, reinforcing the preference for the E2 mechanism over any substitution possibility. Temperature also plays a role. Elimination reactions increase the number of molecules in the system, increasing entropy. Therefore, raising the temperature further tips the scales in favor of E2 over substitution mechanisms. You might wonder about SN1. While tertiary substrates can form stable carbocations for SN1, the presence of a strong base will always drive the reaction toward E2 before the leaving group has a chance to leave on its own. When multiple elimination products are possible, the E2 mechanism typically follows Zaitsev's rule, favoring the more stable, more substituted alkene. This is because the more substituted transition state is lower in energy. To summarize, for tertiary alkyl halides, SN2 is impossible due to steric hindrance. If you add a strong base, E2 is the exclusive result. Substitution only occurs via SN1 if the reagent is a weak nucleophile in a protic solvent. Let's test your knowledge. What happens when we react 2-bromode-2-methylpropane with sodium methoxide? Since it's a tertiary substrate and a strong base, the answer is B, 2-methylpropene, the elimination product. Remember, in the world of tertiary halides, steric bulk is king. It blocks the SN2 path and forces the reaction toward E2. Mastery of these patterns allows you to predict the outcome of complex organic syntheses generated by Vision Solve AI.